Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight, we're going to take a look at exploring some applications of the derivative using TI technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those really tough to teach, tough to learn concepts accessible to all my students. I'm really excited to be joined tonight by Corey Bobby and Tracy Watson. Corey is in his 20th year in education and currently teaches Algebra 2, Geometry, and AP Calculus. Since joining the T-Cube community in 2001, he has worked on curriculum development and workshop instruction, as well as creating online courses and videos for TI-Nspire technology. Corey, thanks so much for being with us.
Oh, there you go. I'm back. Sorry, I had to mute my microphone. Happy to be here.
Thanks, Corey. And Tracy has been teaching geometry, AP statistics, and AP calculus at Benton High School in Arkansas for the past 2 years. Previously, she taught college mathematics courses ranging from basic algebra through calculus for over 15 years. She has been an AP calculus reader for 4 years, which she feels has been the best PD for teaching AP calculus. She was introduced to the graphing calculator as a teaching assistant in graduate school and hasn't turned back. As a T-Cube national instructor, she enjoys sharing with teachers across the country the appropriate use of technology in the classroom. Thanks so much for being with us, Tracy.
Thanks, Mike. It's great to be here with everyone.
We're expecting a large crowd, so your audio is automatically muted. Feel free to send any questions to Tracy or Corey using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. Once we move to the software, that right section of your screen may be replaced with a green floating toolbar. You have the option, if it's not, of maximizing your screen to get the best viewing performance. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once that recording is available, if you'd like to follow along with your handheld or your software, and we truly hope you will, we recommend doing that with the recording. That way you can take your time and go at your own pace, pause, and rewind the recording as necessary. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Corey is going to discuss our agenda.
Well, hello. We're going to start by doing a little welcome and introductions. Like Mike said, I'm Corey Bobby. I'm a high school math teacher in Arkansas, and been with TI for a long time. So we're going to talk through the first half of the applications with the derivatives. Next week they'll be a little bit further, go a little further than, not next week, the next month they'll go in a little further than we will. But tonight we're going to be looking at the relationships between the derivatives, between the first and second derivatives, and what that tells us about the functions. So we'll be doing that on both the Nspire and on the 84. So we'll be looking at graphing the function and its first and second derivatives and exploring the relationships between them. Then we'll move into Rolle's theorem and the mean value theorem and try to come up with ways to help using the technology help students visualize. I don't know how it works in your classroom, but a lot of times my students might be able to work a problem but don't really understand what that means. And then finally, we'll take a look at some motion, particle motion problems, and we'll explore how position, distance, velocity are interacting. At the end, Mike will have some online resources for you. The materials we use will be available to you, and there'll be a webinar giveaway for the registration to the international conference. And I believe if we have time at the end, we'll probably both speak a little bit about the T-Cube International Conference and some of our favorite parts of that.
Corey, thanks so much. Tracy is going to discuss our expected outcomes.
Well, hopefully by the end of the night, we kind of have 3 main outcomes. And these outcomes are really of giving you the ability to explore the connection between functions and their first and second derivatives with your students. So we're going to show you ways that we do that, and we hope then you'll be able to take it to your classroom to do that. The second way outcome is investigating the application of the mean value theorem and Rolle's theorem with your students. So we're going to explore ways that we do it, and hopefully you'll be able to take that to your classroom if it seems to fit. And finally, utilize calculus techniques to solve particle motion problems. So we want to look at those things and how we are going to do that in our classroom.
Thanks, Tracy. It's all yours.
Okay, so I'm going to share my desktop with you. So in just a few minutes, hopefully a minute, you will be seeing the TI-Nspire software that's showing on my computer. And you should just be seeing a screen with the function x squared showing on the screen. So what do you think, Corey?
I am seeing it just fine. We've got the graph of x squared. Yeah, now she and I will be the only ones talking, and we're going to go back and forth. So hopefully everything. I'm gonna be monitoring the chat and the questions. So if you have something very interesting to say, please feel free to ask it in the chat or the Q&A window, and I will. I may stop her. She's not seeing the chat. I'm doing the chat, and Steve has already ratted us out, Tracy.
I see that.
Okay, I don't know if you're, for those of you who are not, we were going to try to play it off, but just so everybody knows, Tracy and I are a married couple. We both teach in Arkansas, so if I slip and call her hun, it's completely okay.
Yeah, it's okay.
So we're going to begin by building the derivative, and I know if you're a calculus teacher, and I know I do this with my kids, we can explore the graphs of the derivative very quickly by having the calculator graph the derivative. And you might be past this where you are. I'm on a block schedule, so I haven't even actually begun the course. I won't get my students until January. So maybe you can go back to this, or maybe you'll use this next year. But what we want to do is we have a simple graph here, just x squared, but we don't say we don't particularly know the derivative yet, or we're trying to discover the derivative. We would like to build the derivative, and so we're going to do that by doing a little bit of geometry on our graphing screen. So Tracy's going to walk you through some of the steps of how to build a tangent line that moves along the graph using the Nspire.
Okay, so I'm going to first start by, I want my tangent line to be controlled by the x-coordinate. So I'm going to go and I'm going to add a point on the x-coordinate. And so now I've got a point on the x-coordinate, and that's going to be what my controller is for this entire document, okay? And so right now we're just working with the Nspire, and we're actually going to take this one and then immediately go to the 84 and show you how you can do not the exact same thing, but something very similar to get the same effect across. So once I've got my point on the x-axis, I am going to draw a perpendicular, construct a perpendicular line through that point perpendicular to the x-axis.
And we're just using interactive geometry on a graphing window, and this is something that would be unique to the Nspire. If she drags that point, the perpendicular will move and still intersect the function.
If I make my line a little bit longer, you can see that. Okay, now where it's intersecting the function, that's where I want to see the tangent line, okay, to my curve x squared. So one of the nice things about this is that is an option under the geometry menu under points and lines is to actually draw a tangent line to a curve. And if I get close to that intersection, TI-Nspire detects, oh, is this the tangent line you want, the intersection of the curve and the vertical, the perpendicular line that I drew? And I do, so I'm going to go ahead and say, yes, that's what I want. Now I'm going to move this equation out of the way. And so here is my tangent line. Now my goal is to graph the derivative function, okay? And so I've got my x and I've got the tangent line that I'm looking at. My derivative function is the slope of the tangent line at that place. So I now need to get the slope of the tangent line. Under the geometry tools, measurement, I can find slopes of lines, including this tangent line that I just drew. And so now I've captured the slope at that particular x. And again, if I move my point, it's moving, the tangent line is changing along with where the point is located to the curve, and my slope is changing.
So we'll be able to, we basically have the x and y for the derivative function. The x is controlled by the point on the x-axis, and the current value of the slope is the y value. So we need to put that, what's currently 1.55, onto the y-axis.
Now this is a really nifty little tool to do that, because I want to record where that 1.55 is on the axis. Under the geometry tools again, if you look under construction, you have this tool called measurement transfer. And it's going to take a number that it will treat as a measurement, and I'm going to transfer it to the y-axis. And so now you can see the point that it added. And if I move my controller point again, then that y value is the slope of that tangent line. Keep that on the screen.
Okay, just stop for 1 second, Tracy. A couple of people have been asking, are we going to be using both the 84 and the Nspire? I just want to make people aware we've begun on the Nspire, but we will be doing some of these. We'll be doing derivatives on the 84, and we'll be actually going back and forth between both platforms.
Yes, we found some good things on the 84. So
yeah, there's a couple people in the chat and the questions have been asking. So
okay.
I just wanted to. You're not seeing that. I wanted to let you just answer that for everybody, so that they don't have to they don't have to worry, and they can they don't have to keep asking individually. Okay.
Okay. So now what I want to do is I want to plot the point that has the x value of my controller, but the y value of this y point. So I'm going to draw a perpendicular. I'm going under the geometry tools again in the construction to grab the perpendicular tool. And I want to be perpendicular to the y-axis through that point, that measurement that I transferred. And so the intersection now of these two perpendicular lines is the value of the derivative function right there. So let me make an intersection point. And I am going to make it stand out. I'm going to change I'm not changing the color. Never mind. Let's just not do that. Okay. So what do I want to do next? Let's see what's happening again. When I change my x value, I'm taking the slope of the tangent line and applying it to this point here. So this point has an x-coordinate, and the y-coordinate is the slope of the tangent line.
So follow the path of that point. It's now, obviously, I don't have my students build this, but it's very helpful to know how to build this, because I want my kids to tell me what is that path of that point what is the path that point is following. And they can pretty much tell pretty clearly that it'll follow a line. But boy, Tracy, you got a mess going on. I mean, would you let me keep our house like this?
No, not really. I would have it clean up if I want my students to focus on this point. There's a lot moving around. So let's hide some stuff. If someone's coming over and I didn't expect them, I'm going to throw a bunch of stuff in the closet. So I'm going to hide all the things that I don't want to focus on. Now, this perpendicular line, I always struggle whether I want to hide it or not. I sort of like it hidden, but then the only thing I worry about is this connection here of this control point. So if I want, and I'm not going to take the time, sometimes I'll draw a little line segment here so they're seeing that connection.
You could pretty these documents up, and sometimes we'll do that, and that's what some of the Math-Inspire documents, but we actually wanted you to be able to take something you might see on a Math-Inspire document and be able to build a little bit of it yourself. So that point that's floating around up in space is a point on the derivative. Those items that you hide are not gone. They're still there. They're just not being, they're still part of the computer software, and they're still part of the document of the build. They're just not being seen. Okay, so
yeah.
Audrey, to answer your question, okay?
Yeah, and one of the things I did a right click on the screen. Under menu, there is a hide show tool that I could turn on, and then you can actually see the stuff grayed out that I hid. And if I wanted to hide more stuff, I could just click on it and it would bring it back. So I kind of was taking a little bit of a shortcut since I'm on the computer software.
Okay.
Now, one last thing that I want to do with this, because I want my kids to kind of see what the path is, and some of them can see, oh yeah, that's a line. Others just get very distracted even by the other movement on the screen. So what I'm going to do is I'm going to do another tool that I just love for this, the geometry trace tool. So I'm going to turn it on. It's under trace, so this one is in a different location than where we found everything else. And I'm going to turn on the geometry trace and point to the geometry object, the point, that I want to leave a trace of when I'm interacting with my document. So now when I interact with that point that is the control point, it's going to leave a path of that point, which remember is on the derivative. And I'm able to now see the actual derivative function.
And we can now look at when the tangent line is positive, where is the derivative? And when the tangent line is has a negative slope, where is the derivative? So we begin all those conversations about the relationship and what's happening when you're at a zero or at a minimum. Okay, all right, Tracy. So we spent now 10 minutes on this, and all we've done is x squared. Come on, hon, let's do something a little.
No, just relax. Because one of the cool things about, I built it just on something very basic, but now it is open to any function that I want to use, because I started off with the function on the screen. That was the basis of my build. And so I'm going to turn off clear the geometry trace because I want to do a brand new one. So I'm going to erase that. And I'm going to graph a different function. So I'm going to go up to my function. And instead of x squared, now do you want something interesting like that?
Yeah, but you need to put that in.
I need to put it where my F1 is because that's where it was built.
Right.
I was just showing you where I was headed.
I know you.
Then x plus 5. So now what I'm doing now is I've changed the first thing that I had on my screen. Now at first, don't worry. It's like, oh, where is it? It's because of my window settings. So I'm going to go back to my standard window. And now I've got the exact same things going on. I've got my control point, and I'm still seeing the tangent line, and I'm seeing the derivative being mapped out.
And we can turn on the geometry trace again and do that same thing.
Oops, wrong point.
Wrong point.
Oop. Control stop. Okay, clear the geometry trace. I can do this. And start that again.
She clicked on the point on the x-axis with the geometry trace, so it was leaving a trail along the x-axis.
Now my derivative point is on top of my control point.
Yeah, you want to position it where it's off of there. There you go, hon.
There's my derivative. Now I can do my geometry trace. I'm not going to hear the end of this.
Yay. For once, I'm not the one who made a mistake. Okay, so you can get creative here and make, Well, and I noticed somebody earlier said they give the instructions to their kids and have them build this. And you can build this on the CAS or the on the regular Nspires. There's no CAS functionality here. And it allows them to, I make a document with many functions, and we can explore several different functions in one. There is value to having kids build this, but that depends upon I probably wouldn't use class time because class time is so precious in an AP course. But it would be a nice home project that they could dig deeper into as well. So,
and just giving them this with it done for one, now I've opened it to any function they want to use. You know, just teaching them that geometry trace. So. And
we picked this function. We just put it in factored form, and we put it a nice coefficient on it so that it would fit in a nice window. Obviously, if we used a bigger, if we didn't have a multiplier or something, we may have to adjust the window, but we wanted to find a function that fit nicely on this window. So that's why if you saw it was a simple function that was already in factored form, we might actually, I might actually come up with a different equation that would be multiplied out, but for the sake of our argument tonight, we wanted it to be quick and easy. But something like that's a real easy way to get it to appear on a nice standard window and still get a polynomial that you can see. Okay?
Okay. Now, this, again, one of the focuses after you start doing derivative is looking at the increasing, decreasing relationship. And so your questions then are going to be about where is it increasing, decreasing the function? What does that mean about the derivative function?
And where's the
investigating that.
Yeah. Where is the derivative positive, and what does that mean for the function? Where is the derivative negative? What does that mean for the function? And so on. Now, after you've done it, I think after you've built it this way, then we can introduce the functionality of the calculator, because the calculator could do this much faster. But having that trail and having them discover will reinforce those derivative rules and help them to internalize them.
And so I'd like to switch over to the 84 now, if you don't mind.
Go for it. Like I had a choice.
Okay. And so now you can see there was a reason I used that particular function. I'm going to use the same function on the 84. Now, I'm not able to build and do any interactivity like I did with the Nspire. But here I've got my graph, and again, this is a pretty nice, it's in a nice standard window. The graph looks really nice because I applied that multiplier. But one of the things you can do with the 84 and get students to practice working with to reinforce the idea, okay, the function's increasing here, what's the derivative going to be? And making that connection is asking the 84 to graph the derivative. And that is on the 84. It's internally doing it numerically, but we're just going to see the whole graph when it finishes graphing. So to do that, if you go under your math menu, you'll notice number 8 is nderive. So it's numerical derivative. And with the OS right now, notice it's in really nice template form. And so we're going to do the derivative with respect to x. Now I am not going to type that function in again. If I hit alpha and then the trace button to get the F4, I get a quick reference to all of my equations on the 84. So I can ask it to take the y1, do its derivative, and then since I want the derivative the whole way, I'm going to do it numerically for every x. And now when I hit graph, I've already graphed the y1. It is working on graphing the derivative at every point, and here it starts coming in.
So after the students have explored it, now on the Nspire, it does this much faster. It just plops the thing in. So I actually like this. It has a similar effect, although they don't control it. I think there's something that's nice about the physical of moving it that helps some children make a connection. But they can still see it develop point by point.
Yeah, I actually appreciate the slowness of it coming in, because I want students to be thinking about what should it look like? Where's it going to come from? Oh, there it is. And kind of predict where is it going to cross the x-axis, and they can start looking at that relationship. Now, one of the nice things that we didn't do on the Nspire that I'm going to do on the 84 is I'm going to graph the second derivative too. right on here. We can explore increasing, decreasing with our first derivative, but our second derivative is handy because of concavity. So I'm going to go back, and now I'm going to, in the Y3, I love the coloring now that we've got all the different colors on the new 84C, and I'm going to ask it to do the derivative of Y2. So same way, math, and derive with respect to X. I'm going to recall Y2 now, because then that will give me the second derivative and do it at every value for X. So now it's taking that and it's doing the second derivative. And again, it's coming in slowly, but I want students, and I remind them, you should be looking at the original graph or even the derivative and try and make connections. Is it what you expect to have happen? And again, I could go back and change the Y1, and everything will change. It will graph the new function, its first derivative and second derivative.
And it's very important for the AP exam that the students talk about the maximums and minimums in relation to the derivative. Tracy and I are both AP graders, and I can't tell you how many points I've taken off for kids writing. There's a maximum at X equals 2 or whatever the case is in this case. I guess it would actually be, we have a maximum at about 2 point something, negative. And what about -3? We have a maximum at X equals -3 because the function changes from increasing to decreasing. That gets you nothing on the AP exam. Yep. What do they have to say, Tracy?
Well, they can't. Do we want to show them?
Oh yeah. Why don't we? Are we ready to look at? Oh, I'm sorry. Do you want to? Yeah. Do you want to skip to student work, or do you want to go back?
It doesn't matter. We've got one more Nspire, and then we got some student work to show you.
Yeah. Why don't we show them the student work since I brought it up? Because we do have we have a maximum. Yeah. I'm sorry. Oh my goodness. Now I changed the agenda.
That's right. Because one of the things that I did is I dug out my tests from last year. And so I usually keep my students' tests for a year or two before I get rid of them. And it's very interesting after a year going back and seeing what your students did. So of course I'm going to show you my best student first that approached explaining what they needed to say properly. So this is one of the first questions that I found that kind of is related to what we're talking about. And it is where they're given the graph of the function, okay? And so they don't know what the equation is, but they have the graph of the function. And so the first thing I asked them to do was to estimate the intervals of the graph where the derivative is positive. And so this is what I got. So what do you think about this, Corey? Did I grade it okay?
Well, this student, I don't know if it's a he or a she, guessing it's probably a he, it's maybe a little messy. It's amazing how you can tell. We're trying to find, the first part, is he talking about the f prime is positive. Where does f prime positive? Well, what are we looking for? We're looking for where the function is increasing. And that only happens from -infinity to -3, so I think you're good. And the student is talking about the function and explaining it in terms of, well, that's not explaining about in terms of the derivative, but is there one here about a maximum and minimum, or is that later on?
Oh, that's the other one.
That's the other one.
There we go.
This is what I was talking about a minute ago. Okay. Yeah, sorry. When a student says that we have a minimum or a maximum or whatever, and this is a very standard, basic question, that, not basic, obviously it's not basic, but it's a pretty common thing where they have to find a maximum. That sign chart is meaningless to me as an AP grader. I love it as a teacher, I love it as a former calculus student, but sign charts are not going to get you the points. You have to explain where the student got the points is here in the wording where he says the maximum is at x equals 3 because the derivative changes from negative to positive. They must explain it in regard to the derivative. And then, so that first check, if Tracy, move your cursor or whatever, that's the point. that's what they must do, okay? And that's what I was saying, and that's what you need to stress. And sign charts are great for organizing their thoughts, but if they don't write it out in something similar to now, they could use F prime instead of using the word derivative, but they must explain it in terms of the derivative. And the way that it was explained to me as a reader was that this is a calculus test. If they say the function changes from increasing to decreasing, that is a pre-calculus explanation of a maximum, and that's not using the calculus to make the justification.
And so then, of course, I found one that didn't do it, and I know I told them they can't just show me a sign chart, because I'm a grader and I know better. And so one of my students had the sign chart identified. That's fine, but then you've got to justify your answer. So this student thought they justified it, but it is not a proper justification. I need to know what you're looking at. And then they didn't even answer the increasing, decreasing part.
But yeah, but the sign chart alone is not sufficient. And even though, to me as a math major and in college math class, this might be sufficient. It even says relative min, but that's not going to cut it.
And then I think I've got one more where they didn't say anything. I mean, they've got this all nice over here. This is much nicer. This one I was trying not to mark their papers up too much. I like to have an F derivative here. There's things they aren't doing that I know I always did in class. But so that was the great.
Yeah, that last one. Can you go back to that last one there? Yeah. F is increasing, and he's talking all around it. This one kind of hurts my heart a little bit because, and it's also a lot of reading that I have to read when all the student has to say is F prime changes from negative to positive. They don't have to write a novel, and this child understands pre-calculus, but is not explaining it in terms of the calculus enough to get the point. So there's a line in the sand that you need to draw to help your students be prepared, and it's that's just the way it goes. I'll talk about
you remember the other thing on this one that you now notice? I gave the points for the increasing, decreasing.
Right.
Corey did not like that too much. He wanted me to make a comment, additional comment to the student on this. You remember? Because they said just because of the slope of the tangent line.
Oh, yes,
they didn't say the tangent line to what?
Yeah, they really do need to be clear, and when they're saying tangent line to, because they could be talking about the tangent line of F, they could be talking about the tangent line of F prime, they could be talking about the tangent line to a circle. I don't know what tangent line you're talking about right now. Thank you for reminding that, huh? We had this argument last night. The tangent line up to what? So I cannot recommend it enough. If you're not already on the the reading list, you need to get in. It was eye-opening how much how picky. It's not that they're very picky. They just have a standard and they stick to it. And if you're not teaching to that, you're not preparing them. So it's just incumbent upon you to either get this training or get to the reading if you can. So anyway, let's. I'm sorry to. It just makes me so happy to share this stuff. So you want to go back and dig into the increasing, decreasing a little more now, since I jumped you out of the agenda. Okay, sorry. Tracy, it's 9:30, so we do need to pick up the pace a little bit, though.
Yep. So do we want to look at this one? We should, because you're going to get it just really quickly, I think.
Yes, let's look at the derivative analysis quickly.
Okay.
Because I don't want to shortchange the other two topics.
Yeah. So let's, derivative analysis, you will get these files, and they're also up on Math-Inspired. But this is one you definitely want to look at, too. So why don't you talk to me about this one, hon?
Okay. I really like this one, and there's, I mean, some of how this is built is beyond what we're going to do tonight, but I think it's fascinating. Here we have, looks to be an odd polynomial, but I'm not exactly sure, maybe some part of a Taylor polynomial, but we're dragging a x-coordinate, and we're looking at the slopes of the tangent lines. And it allows the students to see when the slope of the tangent line is positive and when the slope of the tangent line is negative. Now, if you're in the chat, maybe what questions could you ask your kids to look at based on what they're just seeing on the screen right now? So this is, what are we looking for here is we're looking for, I would ask my students, okay, what's going on when the slope is positive? What's going on when the slope is negative? What's going on with the function? What's going on with f of x? And so you could ask about horizontal tangents, right? What's happening at now? This file doesn't identify slope 0. It would take a little bit of change to make that happen, but it could be done. At any rate, I would hope the students would see that the function is increasing when the slope of the derivative or slope of the tangent line is positive, and the function is decreasing, right, like it is now, when the slope is negative. So as we move, and of course maybe they'd be able to pick up that it's changing from positive to negative or negative to positive at a minimum or a maximum. Okay, so that allows them to make that conjecture. And then when we move into the next one, here it shows them slope is negative and in little segments where it's decreasing. And if you use the slider, it shows you the segments, or the intervals, sorry, the intervals where the function is increasing and the slope is positive. So it's kind of a really elegant document that helps them develop the relationships between increasing and decreasing and positive, negative in the first derivative. And then this particular file goes on to look at the concavity and does it in a similar manner. You can drag it up, drag the x-coordinate across the x-axis and see where it's concave up and concave down. And likewise, it'll do, if you go on, it'll do the intervals of the concavity. So
that's a nice document where that stuff is already pre-built in there.
Okay, so I think we are we done with the first topic? And even though
we're done.
Yeah, okay, because we've got about 15 minutes to look at the other two. So we spent a little more time than we wanted to on the first topic, but that's okay.
We're good.
Yep, okay. So we're going to switch over to the mean value theorem right now. And Tracy has I think you have a typed up question that's just a pretty normal example of a mean value theorem.
Oh, that's right. Yep. There it is.
Okay. So you all probably teach the mean value theorem at some point in this cycle right about now. And the mean value theorem is one of the big theorems that you need to make sure your kids understand and are able to do. So it says that if a function is continuous on a closed interval AB and differentiable on the open interval AB, there exists some value C in the open interval such that f prime of C is equal to f of B minus f of A all over B minus A. And of course, by the time I finish even saying that, half my kids are glassy-eyed. So what does that mean? And I shouldn't have used the word, but what is that actually supposed to do? Well, the mean value theorem basically says that if you have a function that doesn't have any breaks or holes or jumps or any funky business, I'm being very casual now, but I'm not, obviously, we still be formal. We would, as long as you have a continuous function that is differentiable, no cusps or anything, you would be able to find somewhere on that function where the slope of the derivative is equal to the slope of the secant line. So here we have an example where we have x squared on the interval from -1 to 3, and we're trying to find the value of C that satisfies the mean value theorem. So Tracy has the function graphed and the secant line. So she's worked it out, and we've got all this. And if you have good kids who are obedient and good at their algebra, they can get the answer. And I think I do want to, another thing that is really important for the grading, they don't need to do any algebra that they don't have to do. And in fact, if they had written y minus 1 equals 2 times the quantity x minus 1, that would be fine. When they're asked to find an equation of a line, they are not asked to find the equation of the tangent line in slope-intercept form. For one thing you can do to save yourself save your students a lot of headache is tell them to not simplify. If they get that equation that Tracy has on the screen, they will get points. Now, many of them will distribute that too and get 2x minus 1 plus 1 and then report the answer of 2x and get it wrong. If they simplify it and simplify it wrong, they will lose a point that they had. So they don't need to simplify anything beyond getting an answer. Okay, so that's something that you really need to work at with your kids. I try to get my kids to stop and not simplify, but boy, do they love simplifying. And they will stop when they simplify and get it wrong, and I take a point away that they had. So that's a habit that you have to break because they've been trained, and they're well trained, and they're good kids. They want to make you happy, but they do. They've always been told to simplify, get it in a point slope, or get it in the slope-intercept form, and we want them to stop. Okay, so let's go to. You want to show them your 84 trick?
Yeah, and so my kids, you know, they can learn to do this, but do they really understand what it means? Okay, so I've got this that I'm going to graph, and then I'm actually also going to graph my answer. And so on the 84, one of the things, I don't want to take a whole bunch of time because I've used my 84 with this problem. And so I've actually have the problem that I was just showing you for the mean value theorem stored on my 84. So if I do second program to pull up the draw menus and go over to STOW, I can recall what I saved earlier. It's called a GDB, graphical database. And I named this one number 1. Now when I go to my y equals, whoa, everything changed. It is the x squared, it is the secant line, and the tangent line that I was talking about in my mean value theorem problem.
And now she's got a nice window that she's set ahead of time. She's got her secant line and her tangent line, and this will help students visualize what's going on. The red line and the black line are parallel. Why are those lines parallel?
Because they have the same slope, hon.
Oh, yeah, that's right. But wait a second.
That's what the mean value theorem does.
Oh, that's what the mean value theorem does. Oh, so really all that parallel line stuff I did in algebra and geometry has something to do with this. I gotcha. Okay, so that's why I did all that back in algebra. Okay, but the GDB, we were doing some things on the Nspire, and we both use Nspires, but we actually both have sets of 84s and Nspires. They're both great machines, and they both have wonderful applications. But one thing that a lot of people don't know about, and maybe you do, and maybe if you did, but if you didn't, graphical databases are a great way to store some problems that it would have, in front of a group of kids, it would have taken me a few minutes to type these things. And you can actually store up to 10 graphical databases. So you could have a bunch of problems that you're going to use in class set up and ready to go before class, so that you don't have to worry about adjusting windows, you don't have to worry about typing in all these expressions. So you notice she made a nice window for her function and for the viewing. So let's show you everybody how to save a graphical database.
So if you got everything set up of what you want it to be when you unpackage it, I always think of it as a package. Under that second program, which is the draw menu, over under STOW, you've got where you can store a GDB. And so that's what I would want to choose if I want to store another graphical database, another package of graph stuff that I want to open up later. And I'm going to do 2. And now I have that stored a second time under 2.
If she had used 1, it would overwrite the pre. Now, it would have overwritten with the same thing. But be careful if you're going to do this and you have something you really love. When you use it again, it will wipe it out. So, but it's it's something I use in class, and I might use this 6 times this day, and then throw it away and have a couple of these ready to go the next day. But now she goes and you can have.
How many graphical databases do we have available?
It was 10. It was 0 to 9. Or 1 to, well, you go 0 to 9.
Okay.
And then you can now she goes back to y equals and erases everything, changes her window back to Zoom Standard like everybody loves it. And what happens is it would return everything back by just doing the recall. Okay, so it's a quick way of getting a bunch of things in. It's almost, as an Nspire, if you're an Nspire user, you have a document. It's a way of kind of packaging up at least one page of a graphical document on an 84. Okay.
Now let's show them real quick the mean value theorem on the Nspire.
Okay, yeah, and then we got to talk about particle motion.
Okay, so the mean value theorem, again, this is on the Nspire. They've got a nice document for the visualization. So here we've got our secant line that's drawn, and I'm able to change what that secant line is. But if I use the slider, I am turning on all of the tangent lines that have the same slope as that secant line.
And even if you're not an Nspire user, you want to try to get a copy of the Nspire to help your kids visualize. This is such a powerful visual because first of all, they think there can only be one tangent line. Well, now Tracy's got, she's up to 3. Oh, now she's back down to 2. And I bet you she could get a 4th if she really wanted to. Oh, I know. I got a challenge. Okay, so you can visualize, and this is a great visual because kids think there's only one, and when you do one where there's possibly 2, there's like, wait a second, okay? So this gives them a great visual, and as you move the secant line, the tangent line or lines move with it. So here you can turn on and off the tangents, and you can move and see what's happening and where those tangent lines might be. So I love this for the visual purposes, and you would just, you can move. Oh wait, why don't we have one now? This is a math Nspire document. These will be shared with you. A couple of people are asking, where do I get these? Even like I said, even if if this is all you use the Nspire for, use this software. The kids don't have to have the Nspires to see this. You could play with this on your smartboard and have the kids making conjectures, and they can figure, when does it have? Why don't we have a tangent line right now?
What is wrong? The mean value theorem says I should.
There's a point where you don't have differentiability there. I don't know what value that is, but it's between A and B. So what happens if she moves? Oh, there you go. Whoa, wait a second. Go back, back.
Oh, you're gonna make me go back.
Yeah, go back on the other side. Why is she getting one now? Wait, now I'm violating the mean value theorem. Am I violating? Oh, I'm not violating.
You're not violating.
Right.
Just because you don't have the conditions doesn't mean there wouldn't be one.
Yes, so this is a great discussion point. I could still have one, but the only way I'm guaranteed to have one is to meet both conditions. Now I am not getting, now I'm getting one. So this is such a great conversation to have with kids that when we were playing with these documents and when I started using it, this is worth it. So you can get a trial version and go, just drag these around, and those little that little arrows in the upper left turn the tangent lines off and on. So, okay.
So that's another cool one.
And you don't have to build it. All you got to do is be able to click and drag and lead a discussion. All right, we've got 4 minutes.
Particle motion. But this particle motion, it does all the work for us, so that's okay. So I'm going to switch over to another Nspire document to target our particle motion problems.
We would, and we can't do this on a webinar, but in my classroom, either with the 84 or the Nspire, I do want to say I have CBR2s, and if you only have one, that's fine. All you need is one motion detector. having kids move in front of a motion detector talking about rate of change is definitely something you'd want to do, but it's not something that translates well to a webinar. You can't see me moving and see the graph and all that. So a motion detector would be something that I would do before I would do a document like this. Sorry, I just got to say my plug for my science friends.
No. Okay, this one has a little bit of programming in it, but I like what they've programmed because it's opened up some capabilities for us to change the function. So it's defining a position function. So we're just going to start with what they have started with us, 3 sine of t. And then this reset is when we want to start the document over again to try another function. So let's go see what we've got. And this is so hard for me to do in class without this. You know, getting them to really understand the connections of a particle moving on a number line and what the function looks like, the position function and the velocity function. So you're going to talk through this, Corey, because I've got to go steady.
Okay, so she's going to click the slider and move the arrow, and as she clicks the arrow, we're moving along the position graph, and we're seeing the particle moving across the top, and it's moving slower now because the rate of change is slower. But now what is happening as the function is decreasing? Well, the particle is now moving back to the left, and you're seeing it leave a trail. We're seeing the total displacement up there, but we're seeing the current position. Now we're moving backwards. We're moving, now we're going to change direction again. And she's clicking at a steady rate using her, actually the first time she clicked the slider, she clicked it with the arrow, and now she's just clicking the right arrow on her screen. And we're watching the motion of the particle move back and forth. And it's pretty steady back and forth like you would expect from what appears to be a sine curve, well, some manipulation of a sine curve. And we can compare the position graph to its motion, okay? And if we move into the next slide, it does the same thing, but now I have the velocity, and if she's moving backwards in time, and we can reverse the process. And that's what that reset was for on the first page. It would actually reset everything back to 0 and erase the trail. So we're undoing the path here and looking at how the velocity relates to its motion. Okay. Now that's part of what's really cool about this document. But what we were playing with that we really like is, okay, this function obviously looks like some sine curve, but you can redefine that position of t function. So she's going to choose a different definition of the position function. You got to reset, and then that's going to wipe out the trail that we had just made. And if she defines position of t to be some other function, and this function is going to give me a headache. Well, maybe not a headache, but it's not what I would have come up with off the top of my head. So now we go ahead and look at, we planned it. We made sure that it would fit on a nice window. I mean, you could change the window and all, but now we've got something that's not quite as predictable. So what's going to happen now as its position changes, and we're watching the motion, and so as she's moving, if you watch the motion of the particle on the top, it doesn't seem to be moving very much, but if you notice, the graph isn't moving. And because we've done some multiplication of a linear and a sine, we're getting a more interesting function here, and we're seeing the rate of change pick up as those waves get bigger. So as she's moving now, she's still trying to keep a pretty steady rate by clicking at it, click, click, click. You're seeing the particles starting to go faster because the slope is getting steeper. And so we're getting more oscillation, more change. So it really does work to give them a visual of if you can play around with the function. And it does the same thing. It'll do a similar thing with velocity. So, but I do, okay, well, we do have, then you can go to the velocity graph and get a similar kind of visual. We are really pretty much up against our time, so I think we're going to have to leave it right there. There is another version of this. There's 2 files that are in this bundle. One that this one would let you do it with linear segments, and you can still explore and drag those black points that are on the function. You can change them, and it will move everything, and you can see what would happen. Okay, but we're the work's in a similar way, but yeah, we got to let Michael have control back because we're already a couple minutes over. So I just think it was a very fun time to share with you. I hope that you found something that you can use. I know I always judge my workshops and my PD by if I get one idea, I feel like it was success. So my hope is that I've given you one good idea that you can use, and that you have a great evening. Michael, we're going to transfer back to you. I think you guys share back, and then we'll let Michael wrap things up.
Thanks so much, guys. We are going to begin wrapping things up tonight, as Corey said. And if you have any last-minute questions for Tracy or Corey, please try to get those asked. I know they'll do their best to try and get those questions answered. Some people had questions about where these files were coming from, and so I wanted to share where exactly on our website you could find those files. So I'm going to share my desktop. And if you go to education.ti.com and move under the Activities tab near the top, slide down to Math Inspired. Tonight we are focusing on some calculus activities, specifically applications of the derivative on the left-hand side. And so I know one of the activities that was shown tonight was derivative analysis. So if that's one that you wanted to get, you could click on derivative analysis, and it gives a nice little quick video that shows kind of what the students would be expected to go through, so you don't have to necessarily download each file, open it to try and kind of see what the file is about. These little short videos are a great way to explore the file without downloading it. But what I do like is on the right-hand side, you could download all the files if you want. For instance, if there's a TI-Nspire file, which there usually is, and then sometimes there's student and teacher notes along with that. When you leave the webinar, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events. And so please feel free to share your thoughts in the post-webinar survey. I believe Corey mentioned at the very beginning, this is a part one of this type of webinar. We're going to have part two on November 17th. So if you're a typical webinar, TI webinar follower, you know that most of our webinars are on Tuesday nights. But this fall and this coming spring, we're going to have a special calculus-focused webinar series. And it's not going to be every Thursday night, but some Thursdays. So again, the next webinar specific to calculus is going to be November 17th. And if you're interested, you can register for that free webinar on our website. We're really excited that the T-Cubed International Conference is coming to Chicago this year. I'm pretty sure that I'll be there. Corey will probably be there, and Tracy as well.
Yes,
so,
yes.
As Corey kind of mentioned at the beginning, Corey and Tracy, can you guys give a quick 20 seconds as to what your favorite part of the conference is each year?
I love that there's always sessions about, they've been doing sessions topically in the last few years where there's always a calculus session going, there's always a stat session, there's always a geometry session. So no matter what you teach, you can find something every hour and it's on different platforms that fits your needs.
Every session I've gone to, I always get an idea, whether it's from the presenter or from the discussions of the teachers I'm sitting with. Everyone is always so open because we're all there to learn. And so usually sometimes I get kicked out of a room because another session's coming in and other teachers and I are there chatting and excited and want to keep going. So we got to go work out in the hall then. So just the getting together with other teachers that are excited about math and using the technology in their classes. Thanks so much.
So if you'd like to see Tracy or Corey at the T-Cubed International Conference, please feel free to register for that conference. As Corey mentioned earlier, we're going to be giving away tonight to one lucky winner a free registration to the International Conference. And tonight's lucky winner is Brian Liu. So Brian, congratulations. Again, we hope to see you as well as everyone else at the T-Cubed International Conference this year in Chicago. We hope you're excited about some things that you saw tonight, so please feel free to continue that conversation on any of the major social media outlets. you receive a certificate of attendance, please go ahead and click the link in the chat window. If for some reason it's not working for you tonight, have no fear. You'll automatically get a follow-up email within a couple days, and that follow-up email will have a link to the certificate, as well as a link to the documents that were used tonight, and a link to the recording as well. So you get all three in your email within a few days, just in case that link isn't working for you tonight. And if you're watching this on demand, please feel free to copy that link down into your favorite browser to receive your certificates. Thanks so much, Corey and Tracy, for everything you shared tonight. Corey, I learned something tonight, so I'm going to call this a success. So thank you both for everything that you did, sharing everything tonight.
My pleasure. I enjoyed it.
Thanks, Mike. It was great.
Thanks again, everyone. We hope to see you back online next week. Have a great night.